Hi, and thank you for watching this video on my ECE3400 Project 1. The goal of this project is to become familiar with MOSFETs by working with experimental data and building SPICE models. Let's begin by looking at the given data. First is the channel current of an NFET versus gate voltage with the source at ground and drain at 2.4 volts. It looks like this. We would like to know its threshold voltage. This can be found by noting that as Vg exceeds the threshold, the current becomes quadratic behavior. So we can take the square root of the given data and apply a linear fit. Note the quadratic assumption is imperfect. Nevertheless, the beginning of the threshold region can be thought of as linear. The line parameters calculated with MATLAB are shown. We use the x-intercept as an approximation for the threshold voltage, and note for later this relationship. The square root of k times kappa over 2 equals 0.0063. Furthermore, from the data, when the gate voltage equals the threshold voltage, we get a threshold current of about 36 nanoamps. Next, we look at below threshold behavior. By noting that the current below threshold is exponential, let's look at the logarithm of the first graph. We can again apply a linear fit. Here UT is the thermal voltage, which at the temperature the data was taken has a value of 25.8 millivolts. From this, we can also get a subthreshold kappa of 0.6315. From the data, we can also observe the transconductance Gm, which is defined as the change in current over the change in input voltage. This graph shows the ratio of transconductance to current versus current, with the horizontal axis plotted on a log scale. Next, we look at the current versus source voltage with gate and drain at 2.4 volts and the bulk at ground. Again, above threshold is roughly quadratic, so we look at the square root graph. Applying another fit, we can get another expression using only k and kappa, which is that square root of k over 2 kappa equals 0.0079. Using the expression from the previous fit along with this one gives k and kappa as shown. As before, we examine the subthreshold region where the current is exponential using the logarithm graph. Applying a fit, we can get an estimate of the thermal voltage, which differs from the nominal value of 25.8 by about 14%. The last measurements for the NFET is the drain sweep, keeping everything else constant. Again, let's see this in log scale. Applying a linear fit, we can get a value for VA, the early voltage, of 37 volts. We can use the parameters we've collected along the way to perform a SPICE simulation. They are listed in the table as shown. We needed phi and gamma, and we note that we can get those by satisfying this expression shown in the bottom left. To the right is the circuit used during the simulations. These graphs will show the SPICE simulations, given data and fit, superimposed on one graph. This first set shows the gate sweep in square root scale and log scale respectively. It appears to be a good fit. This set shows the source sweep, which around lower voltages look appropriate, but starts to fall apart at higher voltages. The last set shows the drain sweep, which unfortunately is off by a few orders. There are corresponding data for a PFET. In the next slides, Next slides show the result of similar steps taken with the NFET to produce a spice simulation. Unfortunately, despite my best efforts, I was not able to replicate the given data, and the simulations vary from a few multiples to a few orders off in error. This first step shows the gate sweep, in square root and log scale respectively. Again, like the NFET, here's a transconductance graph. This set shows the source sweep, and this shows the drain sweep, as well as the spice parameters used for this simulation.